Good morning, students. Welcome back to our YouTube channel, School for All. So today we are still under Advanced Level Physics. Yeah, because I'm a physics teacher. So we will now see. We will still be on circuit problems, but now we'll talk about capacitors in parallel and in series. So we are still on circuit problems, capacitor in parallel and in series. As usual, I will start with a small record. Before applying the small record with a small example. So the first record that we should know here is that C, the capacitance of a capacitor. We all know that what a capacitor is that electric component that is used to store what charges, and the capacitance of a capacitor is the ability of that capacitor to store charges. So and that capacitance is Q all over V. Now let us see how we can connect capacitors in parallel. So let's talk about parallel connection. Parallel connection of two capacitors. So parallel connection of two capacitors. So when you have two capacitors connected in parallel like this, two capacitors connected in parallel, so this is how we connect two capacitors in parallel. Then we place a small cell here to provide a PD of V. Let's call this one C1 and this one C2. Okay. We all know that what? When two capacitors are connected in parallel, the first capacitor C1 with its voltage V1 and this one C2 with its voltage V2. We all see that what? The PD here is the same as this one here, since they are in parallel. So V is simply equals to V1, which is the same as V2. So that is the first information that we should know when we are having two capacitors in parallel. Also, we know that the charges, we know all that our charge is current. Charge is IT. So it is still current. So it means that the charge delivered by this cell, it is Q. This is here, Q. It will split into two, Q1 and Q2. So we split into two, Q1 and Q2 exactly as current. Now, we agree earlier that the Q which is being shared between C1 and C2 is simply equals to Q1 plus Q2 by applying what we call Kirchhoff current law. At this note here, Q is Q1 plus Q2. As we said before, anytime we are seeing a current which is being shared or a current which is being divided, you apply what current divider. But here we are having what charge. This charge Q is being shared between C1 and C2. Therefore, I will apply what charge divider. Let us apply charge divider. Charge divider. We see that what this charge Q will be divided between C1 and C2 in the ratio C1 is to C2. Are you seeing it? C1 and C2 in the ratio C1 is to C2. Now another important thing is that if I want to calculate the total capacitance of the circuit, the total capacitance of the circuit here is exactly the inverse as in resistance. Like when we are having resistors in parallel, we do product over sum. But here, when you are having capacitors in parallel, it's like you are having resistors in series. So C total is what? C1 plus C2, sum of the capacitance. So that is it. So C total here for capacitors in parallel is the same, exactly the same as for resistors in series. So C total here is C1 plus C2. So let us come back to the charge divider. It means if I want to calculate the charge that flows through C1, that is Q1, this charge, since this charge Q, that is Q total, is being shared between C1 and C2 in the ratio C is to C1. Therefore, Q1 is simply equal to C1 over C1 plus C2 times total charge Q. Yeah, we did it already when I was doing current divider in our previous video. So those that are understanding how I'm sharing this Q into between C1 and C2, you should go and see. It's exactly when I was doing current divider law, how to share current through two resistors in parallel. So it's the same thing. So now if I want to find out Q2 will be simply equal to now C2, since I'm sharing to Q2, C1 plus C2 times the voltage being shared with is Q. So that is it. So this is how I apply charge divider to find the charge flowing on C1 and the charge flowing on C2. No need to find the charge flowing on V1 and V2. No, it's exactly equal to the PD across the cell because they are all in parallel. Okay, now I think this is more recalled under parallel connection of two capacitors. Now let us go to series connection of two capacitors. For series connection of two capacitors, series connection of two capacitors. Series connection of two capacitors. So I'm having C1 connected to C2 in series. Then I connect a PD across them like this. Then I connect a PD across them. V. This is V. We all agree that here the voltage are not the same because they are in series. When we are having component in series, they don't have the same voltage, but they share the same voltage in proportion to the value of their capacitance right here. So what I know is that the total charge flowing is the same as the charge flowing through C1, which is the same as the charge flowing through C2. You all see that the charge flowing here will pass through those two capacitors. But we see that for V is different. Yeah, it's different because the voltage here is not the same as here. No, since they are in series, they will share this voltage in proportion to what? The value of their capacitance. But it will be different, like the potential divider from resistors. So let me apply potential divider. It will be different because here the voltage is being shared in the ratio 1 is to C1 is to 1 is to C2. Why am I saying that? Why am I saying that it's being shared in the ratio 1 is to C1 is to 1 is to C2? Because the total capacitance of the circuit is is 1 over C total equals 1 over C1 plus 1 over C2, which is the same as product all over sum, as you usually see in O-level, product all over sum. So that is it. It means that for series connection of capacitors, we are having reciprocal capacitors. So that is 1 over C1 plus 1 over C2, product all over sum. So if I want to share this voltage between these two, I should take 1 over C1 is 1 over C2. So it means that my V1 is simply equals to, I told you, I will take 1 over C1, 1 over 1 over C1 plus 1 over C2 times V. And this, after simplification, we come out with C2 all over C1 plus C2 times the voltage being shared. Without wasting time, we do same. So as you see, when we have 1 over C1 is 1 over C2, always start, when you're looking for V1, you start directly with C2. Now, if I'm looking out for V2, I will start directly with C1. So that is it. So that is it about those are the information that you should know about the series connection of two capacitors. Okay, now let us proceed now with a small example in order to apply what we are just from doing. So what example? June 2014, question 2. Having the circuit diagram. Number 1, we are having a circuit. Now, they are asking us A. Calculate the charge stored in the 4 microfarad capacitor. B. The potential difference across Y, Z. So calculate A. We want the charge stored under the 4 microfarads. Now look at where is the 4 microfarad? Let us identify. This is our 4 microfarad. We all agree that this one is a positive term. It means that the charge will flow like this. The total charge is flowing here and come and split here into 2. Pure 1, pure 2. So the charge flowing through the 4 microfarad is pure 1. Is simply pure 2. And we all know that what? Anytime I'm having a charge divider, I should apply. Anytime I'm having the charge divided into 2, I should apply charge divider, which says I will share this pure total between 4 microfarad and 5 microfarad. So I will share it between 4 microfarad is to 5 microfarad. So let us apply the formula that I just from seeing. It means that I will have 4 microfarad all over 4 microfarad plus 5 microfarad times the total charge is being shared pure total. So that is it. So it means that pure 2 is simply equal to those microfarad we cancel is 4 all over 9 pure 2. But we need to find pure total. We need to find pure total. We are not having pure total. But I know that from the formula of capacitance of a capacitor, C equals to pure all over V. This implies my pure total, I want to make sure it's up to here. You simply C total times the PD across the circuit. PD 90 volts. C total. Are you having C total? No. Sugar calculate C total. C total. In order for us to calculate C total here, we all know that one C total. We identify these two are in parallel. Remember, when we are having parallel connection of capacitors, it's the same as series connection of resistors. So I will find the equivalent here, then I will come and do series connection with this one. So these two are in parallel and the equivalent here will be in series with the 3 microfarad. So it means that I will have it means I will have 3 microfarad times in bracket. They are in parallel, therefore I should add them farad plus 5 microfarad divided by 3 microfarad times 4 microfarad plus 5 microfarads. Oh yeah, you understand what I'm doing? It means that these two are in parallel, therefore I will sum them to find the equivalent. Then the equivalent here is in parallel with this one, therefore we put up all over sum value. Here is plus. Put up all over sum. So we will have here those microfarad, we go up and move it. I will have here 3 times 4 plus 5 is 9 all over 3 plus 9. So 3 times 27 all over 12. All over 12 what? Microfarads. So my C total is simply equals to, I think 3 can cancel how many times? 9. 3 cancel how many? 4. So it's simply equals to 9 all over 4 microfarad. So this is my C total. With my value of C total, I will come now and replace C total here to find Q total. So let us remember C total, let us put here, C total is 9 all over 4 microfarads. So it means our Q total is simply equals to 9 over 4 microfarad times C, which is how many? 90 volts. Okay, C, which is 90 volts. So I will have so after dividing, I will have 9 divided by 4 times 90 will give us 202.5 microcoulombs. So that is it. That's my Q total. Let me put it here. So Q total is simply equals to 202.5 microcoulomb. So with my value of Q total now, I can now finally find Q2. So this implies Q2 is simply equals to 4 all over 9 times 202.5. So Q2 will be simply equals to, let us sponge, times 4 divided by 9. So it's simply equals to 90. It's simply equals to 90 microcoulombs. That is the answer. Don't forget here is microcoulombs, making the answer here to be 90 microcoulombs. So that is it, as simple as that. Very quickly, I came out with the value of Q, a charge flowing through the 4 ohm, the 4 microfarad, pardon. The charge flowing through the 4 microfarads. So the big part of the question is asking us to find the potential difference across YZ. Where is YZ? Is it YZ? Across these 2 points YZ, you want the potential difference across YZ. Okay. So we are having, we are having 2 branches here, X, Y, and YZ, which are in series. The branches are in series. Okay. It means that they are sharing 90 volts. And we all know that what? If they are sharing 90 volts, it means that this 90 volts is simply because the voltage across XY plus the voltage across YZ. That's it. And we are looking for the voltage across YZ. Okay? So the voltage across YZ is simply equals to 90 volts minus the voltage across XY. Are we having the voltage across SY? No. We don't have the voltage across XY. Question mark. So I should come and find the voltage across SY. Voltage across SY is the same as the voltage across one. The voltage across SY is simply the same as the voltage across the 3 microfarad capacitor. It's the same as the voltage across the 3 microfarad capacitor. So from C equals to 1, Q on V implies the voltage across the 3 microfarad is simply equals to, if I make V here the subject, is simply equals to the charge flowing to the 3 microfarad, and that charge is who? Is this Q total coming from the battery? So Q total divided by the capacitance of the 3 microfarad is who? The capacitor of the 3 microfarad is simply 3 microfarad. So I will come and put my 3 microfarad. So I need now to find Q total. But I know the value of Q total. We calculated the value of Q total here, if you remember. But Pure total is simply equals to 202.5 microcoulombs. So making this value to be simply equals to 202.5 microcoulombs divided by 3 microfarads. So that micro will cancel. So the voltage across the 3 microfarad will simply be, okay, let us sponge. After numerical application, we have 202.5 divided by 3 is simply equals to 67.5 volts. So if I have now, let me put it here, the voltage across the 3 microfarad is the same as the voltage across X, Y, which is equal to 67.5 volts. If you are having VXY directly, you can come and find directly the value of VYZ as required in the equation. So my VYZ will be simply equal to 90 volts minus 67.5 volts. So after subtracting this, we'll come out with 22.5 volts. So that is it. So that is the voltage across the branch YZ. As easy as that. So if you people master your charge and potential divider, it will be very easy for you to come out with those values, or it will be very easy for you to solve question under capacitors. And also for those that don't master the potential divider law and the current divider law, you should go and watch the previous video. Yes, I did a very detailed recall there. It will help you for the other questions. So see you later for another past question under circuit problem capacitors in parallel and in series. We are together.